to more trig substitution?
Yeah, we tried homework 60, and we got most of it right, but it's some of the numbers, like, we'll have stuff over 2, and then for them, the 2 is gone. It's small stuff like that that we kept.
Okay, let me hold off on those, because we may work that out. If we have time at the end, then that's the trig substitution homework, right? So let me come back to that, because I want to make sure we get a chance to work through all of that stuff. Alec, did you have something earlier than 60, or was yours?
I thought I did, but I might have figured it out, because there's one I was working on this morning that I was going to move. But I think I erased the circle on it, so I think I figured it out. So I think I should, yeah.
Okay, so let me I'm going to pick up with we kind of got halfway through one at the end of class yesterday, if you watched the classroom video. So I'm going to pick it up right from there, and then we'll work through this. So we were trying to do the integral of 1 over the square root of 4 plus 9x squared dx. So we can see this is something we can't do any other way. So you can't do a u substitution, because if we let u be the inside, there's no x to call du in the numerator. It doesn't fit with inverse trig function, because with the plus sign, we need to not have the radical to be an inverse tangent. And with the radical, we need a minus sign there, and we can't create that. So we're stuck, except that now we know trig substitution. So because it's the sum in the radical, that tells us that we must call the hypotenuse that radical. That's the square root of 4 plus 9x squared. Now the 2 legs of the triangle, one is going to be the square root of 4, and the other one's going to be the square root of 9x squared. So if you don't get it right, then you just fix it, because we want the x ultimately to be a sine, a tangent, or a secant. So I think if we plug 3x here, that's the square root of 9x squared, and the 2 here, then the trig function that connects the x term with the constant is going to be a tangent. So we have tangent of theta is opposite over adjacent. So we want to solve for the x so that we can get the dx. So we're going to multiply by the reciprocal, so that's going to be 2/3 tangent of theta. Now we're going to take the dx, because we got to replace this dx by something with thetas in it. So really taking dx d theta, but we're going to multiply the d theta over. So the derivative of tangent of theta is secant squared of theta. And then we're going to multiply that d theta to here. So now we're going to be able to replace the dx by all that expression there that's got thetas in it. We need an expression for the radical, because that's part of our integrand. So the radical, we want to connect with the constant, and the trig function that connects those, if we did an adjacent over hypotenuse, that would be a cosine, but we don't want that in the denominator. So we're going to call it a secant of theta. So secant of theta is going to be the radical that we're trying to get an expression for over the constant 2. So we can multiply that 2 to the other side, and we can get our radical in terms of theta. Okay, I think that's everything we need. So our integral now is going to become, so I'm going to put the dx in the numerator there, and so that's this whole 2/3 secant squared theta. So 2/3 secant squared theta d theta. The radical, we said, was a 2 secant theta. And so we can clean up. I think the 2 can cancel with the 2 in the numerator. We can pull that out as a 1/3. One of the secants will cancel, and we're going to get our integral of secant theta d theta. And this is an integral we know. I say, with hope in my voice.
Natural log.
Natural log.
Absolute value of secant theta plus.
Nice. And then we don't leave it with the thetas. Now we go back to our triangle and go back to the x's. So we're going to get the 1/3 natural log. Now secant, we said was hypotenuse over adjacent. So that's going to be the square root of 4 plus 9x squared. Well, I think this might be one like where you were talking about. I think I know what you're talking about, Austin. Plus our tangent of theta, which is opposite over adjacent. 3x over 2 plus c. Now, this would be the correct answer. I don't think this is going to be like this. If this was a problem that you were checking the answer in the back, you wouldn't see this answer, because here's what they are going to do. They are going to use a property of logarithms here. They're going to say, we're going to combine this, we'll condense this into a single fraction inside that logarithm. So they're going to write it like this. Then they're going to say the logarithm of a quotient is going to be the log of the numerator minus the log of the denominator. So that's going to be 1/3 natural log of square root of 4 plus 9x squared plus 3x. Then they will say minus the natural log of 2 plus c. But then they're going to say that's just a constant. It's included there. And so that's why they're not, you won't see that written at all. And then you'll say, well, wait, my answer is off by a constant, the over 2 or whatever it might be, and it's because of that kind of simplification that they're using that I wouldn't expect you to do. I mean, you could, that'd be great.
Would
But
a
it's not.
test expect us to do that?
You won't, with my test won't expect you to do that. I mean, if you do, great, but if you don't, it's equally correct. These are all correct answers, I don't care. And this isn't an AP topic, so you won't see anything with trig substitution on the AP exam.
Answers all of our questions.
All right, very good. Well, let's do another one. So, let's do the integral of the square root of 25x squared minus 16, 25x squared minus 16 all over x dx. Okay. Now, because we have a radical, I mean, we can't do this any other way. We can't do it with a substitution. It's not an inverse trig function. So we were thinking trig substitution here. And because in our radical we have this thing minus that, the term that precedes the subtraction, we're going to name its square root as our hypotenuse. So the hypotenuse is going to have to be 5x. Now, one of the sides is going to be the square root of 16. The other side is going to be the radical. And these are the ones that I don't always get right. So I don't know, but we'll check it out in a minute. I'm going to say, put the 4 here for now, and the square root of 25x squared minus 16 here. So if we try that, then to get x, we would have to connect the term with the x in it with the constant. So that's the opposite side in the hypotenuse. But we want the constant in the denominator. So to go hypotenuse over opposite would be a cosecant, and that's not what we want, because we want our x to be sine, tangent, or secant. So that means I didn't put these in the right place. So I'm just going to switch them. Does that make sense? It's kind of a strange way to think of it. But I'm going to go 4 here, and then the square root of 25x squared minus 16 there. Now, to connect the x term with the constant 4, we're going to call that a secant. So a secant of theta is hypotenuse over adjacent. We want to get the x by itself. So we'll multiply by the reciprocal to the other side. And that's going to make that be 4/5 secant theta. We need an expression for dx. So we'll differentiate dx. So dx is going to be 4/5 secant theta, tangent theta, and we'll put the d theta there. So we've got our dx that we need, we've got our x that we need the radical. So we're going to partner the radical with our constant, and that's going to be the trig function tangent. So tangent theta is the radical that we're trying to get over 4. So 4 tangent theta is going to be our radical, 25x squared minus 16. Now we can change our integral from x's to thetas. So the radical is going to become 4 tangent theta. The dx is going to be all of this 4/5 secant theta, tangent theta, d theta. And the x is the 4/5 secant theta. So we have transformed our integral from x's and dx's to thetas and d thetas. So what can we cancel? I guess we get rid of the 4/5. We can get rid of that secant. Yeah, good. The 4 we can pull out. And now's where we're back to the stuff we were doing in section 7.3, where you have that sheet if you need it. Does that look okay? You remember what to do with tangent squared? Exactly. And if not, you can use your sheet. So I'm totally okay with that. You'll have that available. So tangent squared, if you remember, if we divide through by cosine squared, we get tangent squared plus 1 is secant squared. So tangent squared is secant squared theta minus 1. So that is going to become, or tangent theta, that's going to be minus 4 theta.
Because you're still
Taking the integral.
You're taking the integral still based on theta. So you would split
Oh,
that apart.
yeah, no, yeah, I know. I see.
Okay. Okay, so far. Now we got to go back to the x's. So tangent theta, actually for tangent theta, we said there's our radical. So that's going to be just the square root of 25x squared minus 16. And here's where it gets maybe a little weird, I don't know. Theta, let's see. Secant theta is here, is 5x over 4. So theta would be the arc secant. So we're going to get theta is arc secant of 5x over 4. So that's a 4 arc secant of 5x over 4 plus c. Crazy. You okay with that?
Yep.
Okay, so let's do another one. Let's do the integral of dx over x squared times the square root of 9 minus x squared. See if you can draw your triangle and label it. I'm going to pause the video for a moment so our virtual listeners can do the same. So because we have a square root of 9 minus x squared, what precedes the minus sign, we're going to take its square root and call that the hypotenuse. Now, the other two sides, one of the sides is going to be x, and the other one is going to be that radical. So the question is, does the x go here and the radical there, or the other way around? And if you don't, I mean, we just guess. I don't know, let's say x goes there and the radical goes here. Now, what we're trying to do is match the x with the constant and hope that that's going to be a sine, a tangent, or a secant. If it is, we chose right. If it isn't, we're just going to switch them and it should fix it. So the trig function that connects the x with the constant is going to be and that's what we want. So we had a 50-50 chance, and we got it right. So sine theta is x over 3. So x is, and then what are we going to do with the 3 sine theta, the x derivative? Take the derivative. So dx is going to be, okay, good, and there's our d theta. What else do we need to get? The radical. So how are we going to get the radical? We want to partner it up with the constant. So what trig function connects the radical? What's that? Okay, good. So cosine theta is going to be the radical over 3. So our radical is going to be 3 cosine theta. I think that's everything we need. So our integral is going to have the dx on top, the 3 cosine theta d theta. We're going to have an x squared. So when we square our expression for x, that's going to become good. And our radical, good. And there's our new integral. 3 cosine theta is our history. That comes out as 1/9. And we're going to think of 1 over sine squared as which is going to be a negative cotangent theta. So we go back to our triangle, and so we're going to get, for a cotangent of theta, tangent is opposite over adjacent, so cotangent is going to be adjacent over opposite. So that's going to be square root of 9 minus x squared over x, and then we have that 9 from the 1/9, and then our plus c. Let's do another one. So we have the integral of dx over the square root of 4x squared plus 1. Alec, how do we start? Say it again, I'm sorry.
The whole radical.
Yeah, good, exactly. In the other two sides, one of them is going to be, and you want to go with the 2x here.
Yeah.
I think that's a good choice, because then what connects our x with the constant is a tangent. And so x will be 1/2 tangent. what?
Take the derivative of it.
And derivative of tangent. And what else do we need?
Theoretical.
And so our radical is going to be, well, we don't want it in the denominator though, so it'll be secant.
Yeah.
So secant theta will be our radical. All right, so the dx is our 1/2 secant squared theta d theta. Our radical is a secant of theta. So yes, we've got 1/2 the integral of secant theta. And I think we have agreed that is going to be a logarithm of secant theta plus tangent theta. And we'll go back to our triangle and say secant theta is going to be good. And the tangent of theta is, there we have it. Okay, so let's, a couple twists we can add to this. One is we can deal with some things that aren't just straight radicals, but things that we can think of as powers of radicals. So if we had something like, say, so we can extend trig substitution to things like, say, a squared minus u squared to the n over 2. So we add it to the 3 halves or to the 5 halves or to the 7 halves. We could think of that as being the radical that we're used to a power. And then we can still proceed using trig substitution. So try one like that. Let's do the integral of dx over x squared plus 1 to the 3 halves power. Okay. So do you want to rewrite that? I don't know if that helps or not to think of that as the root of x squared plus 1 to the 3rd. So now we got to still do our whole, how are we going to label our triangle? Good. And one side is going to be good, and you pick them in the right order so that we can see that sine theta is our x, and so dx, good, and our, nice. I think we're ready to call this, the dx is going to be our cosine theta d theta. And we're going to get our radical, which is secant theta.
Which just makes it cosine squared.
Wait a minute now.
Oh, yeah.
It's cubed theta.
I missed something.
Where did I
But the
read?
x, why is sine of theta equal to x?
Ah,
Would that be
ah.
tangent theta?
Yeah, that makes a total, yes, thank you. Tangent theta is x, so dx is going to be, well, this is going to help our cause.
Things are about
This
to be
is
a
good
little
news.
dicey.
Very good news.
So we get secant over secant cubed.
Oh, good.
Or secant squared over secant cubed.
Secant over secant.
And that's a secant cube, does that look right?
Yeah.
Oh, this is good news. Well, the integral became almost embarrassingly easy because 1 over secant is indeed, oh,
Angles or something.
yes.
So that's, we don't have to plug that back in.
Yeah, we do.
Okay,
So sine theta is gonna be,
That is
very nice. Okay, so if you saw the video, we said when we make this tangent theta, if we do a substitution that leads to tangent theta being a radical, and we have a definite integral, we have a potential problem. So let's talk about an example of where that can come into play. And then we'll talk about how we can resolve it. Okay, converting limits of integration. So we'll look at an integral from square root of 3 to 2, and we'll go square root of x squared minus 3 all over x dx. So here we have a definite integral. And we'll get to that part eventually. First, it's another trig substitution problem. So as before, we're trying to figure out how we're going to label the sides on our right triangle. And the hypotenuse is going to be dx. Okay. The other two sides, one side is going to be, and the other side is going to be the radical. So the question is, where do we put this? So I guess the question is, where are you going to put the constant? So I think we want on the bottom, because then x over the constant is going to be hypotenuse over adjacent, which will make that a secant. And that's what we want, because we want either a sine, a tangent, or a secant. So by default, that makes the other side the radical. Okay, so then we can say that secant theta is x over the square root of 3. So x is going to be 1 over square root of 3 secant theta. So that will make dx. Good. So we got secant theta, tangent theta, d theta with our constant 1 over square root of 3.
Mr. Street, should you multiply by square root of 3? So it should be square root of 3 secant theta instead of
Ah,
square root of 3?
yes, yes, yes. Oh boy, that would have made a difference in a moment here. Yes, thank you. Let's nip those errors before they get to be monumental. Good. And we need a radical. So the radical is going to be, we're going to make that connect with our constant. So tangent of theta is our radical over our constant. So that's going to be square root of 3 tangent theta. That look okay? Okay, now we're going to make our substitutions for the, like we did before, but then we're also going to change our limits to theta limits. So this is going to become, I'm going to leave the limits for a minute. We're going to come back to that. The radical, we said, is square root of 3 tangent theta. The dx, we said, is square root of 3 secant theta, tangent theta, d theta. And that x was square root of 3 secant theta. So this part is easy enough, but let's hold on a minute. Well, I guess we can, we're gonna put here, we're gonna take theta of square root of 3 and theta of 2. So we're going to come back to those. So this will be just our square root of 3 coming out. Our tangent squared theta d theta we'll talk about in a moment. And so now what we want to do is say when x is 2. So we're going to come back to, I guess we can come back right here if either of these will work. So we can say here that secant theta is, and we're going to plug in the 2 we had for x over square root of 3, and know that secant theta is 1 over cosine theta. So to solve this for theta, we can take the reciprocal of both sides, and so we'll get cosine theta is square root of 3 over 2. It's a good thing that we fixed all of that stuff earlier. And so theta is going to be 5 over 6.
5 over 6.
Good. So that was our theta of 2. So this is going to be a pi over 6 here. You with me? I'm going to put the square root of 3 in there. So we're going to get here, we're going to get secant theta is square root of 3 over square root of 3. Making secant theta 1. And since secant theta is 1 over cosine theta, taking the reciprocal of both sides still gives us cosine theta is equal to 1, meaning theta must be 0. So changing these limits, now here is the thing where you have to think. Once we have changed these limits, we see that these limits are going to put us in quadrant 1. The thing that we're checking for is where we have this radical. So we have to make sure that our radical is going to always be non-negative. We said that x is equal to square root of 3 secant theta. So for secant theta, its domain is going to be 0 to pi. That'll give us 1 of everything that a cosine is going to do. Quadrant 1's where we're going to get the positives. Quadrant 2 will get the negatives. We got to make sure now if we're between 0 and pi, then we have potential concerns here for tangent. If our limits were in quadrant 2, we would be saying, in quadrant 2 tangent's negative, we would be saying the radical is equal to a negative, which isn't possible. But our limits are in quadrant 1. So this is not an issue for us because in quadrant 1, tangent is positive, and so this is a valid substitution, and we can just heave a big sigh of relief and proceed.
And if it isn't, we just have to specify that?
We'll come back to it. Then what we're going to have to do is change that to make it the negative of tangent if our limits are going to put us in quadrant 2. So we'll go ahead and finish this up because we're almost done now. And then we'll come back and I'll just change the original problem that's going to then make us have limits that are going to put us in quadrant 2, and we'll just see what that does for us. So integral of tangent squared, we said we're going to replace that with secant squared theta minus 1. Okay. The integral of secant squared is tangent theta. The integral of 1 with respect to theta is theta, and we're going to evaluate that from 0 to pi over 6. So we're going to get the square root of 3 times tangent of pi over 6 minus pi over 6. And from that, we'll subtract in the tangent of 0 is 0. That's going to be 0 as well, so we don't have to worry about the lower limit. Tangent of pi over 6 is going to be sine pi over 6 over cosine pi over 6, which is, so we just call 1 over square root of 3. Should we just leave it like that? I think that's going to be a good thing. So we have 1 over square root of 3 minus pi over 6. So that's going to give us 1 minus, well, there you have it, pi square root of 3 over 6. Crazy. Okay. Now, let's doctor the problem up a little bit. So we're going to keep our same integrand, but now we're going to change the limits so that they will go from -2 to negative square root of 3. Okay? So our triangle doesn't change. I mean, the integrand is still the same. So we still set it up the same way. We still make our same choices for what theta is, for what x is, dx, and so on. We make our substitutions in here as we did before. The integrand still substitutes, although we're going to come back to this in a minute because we're going to have to make an adjustment. Now, here's where it gets interesting, because now we're going to take theta of negative square root of 3, and this is going to be theta of -2. So now we're saying so now we're going to change our limits here. And so we're getting secant theta is going to be, so here if we plug in negative square root of 3 over square root of 3, that's -1. So if we have 1 over cosine theta is -1, that's going to be cosine theta is equal to -1. The theta is now going to be pi. So this has now switched to pi as our upper limit. Okay? Similarly, now if we plug in the -2, we have secant theta is -2 over square root of 3, which means cosine theta is negative square root of 3 over 2. So the angle where cosine is negative square root of 3 over 2 is going to be 5 pi over 6. So this has become 5 pi over 6. Now is where we have to halt for a moment and recalibrate. Because these limits put us into quadrant 2, that means where we're saying this radical is equal to square root of 3 tangent theta is not accurate as it is right now, because tangent of theta in our interval in quadrant 2 is negative. But this radical cannot be a negative. Therefore, we're going to fix it by making that a negative. Because now it's okay on this domain.
Okay.
Nothing else had a problem on that domain because we didn't care about those others. You know, x is free to be whatever it wants to be, positive, negative, it doesn't matter.
And if the domain crosses two quadrants?
It can't, because to do that it would have to cross over pi over 2, which is a discontinuity.
Okay.
Because tangent there is going to be infinite, as be undefined. So we can't have an interval that's going to cross over from quadrant 1 to quadrant. They like have a lower limit in quadrant 1 and an upper limit in quadrant 2. So that means when we did our substitution up here, the part where we put in square root of 3 tangent theta, now we have to put in a little negative there. And so that means it's going to pass right on through. Okay? And so then what we're going to get is we're still going to have, I'm going to have to erase this. We're going to get a slightly different answer because we have a different domain that we're integrating over. So there's no reason to think these would be identical. So now we're going to have our negative here. So this negative comes through. Our limits are now 5 pi over 6 to pi. We're still getting tangent of theta minus theta. Tangent of theta minus theta. And now we're multiplying by a negative square root of 3. And now we're evaluating from 5 pi over 6 to pi. is more complicated because now we have a negative square root of 3. So we have tangent of pi minus pi, and then we're going to subtract from that tangent of 5 pi over 6 minus 5 pi over 6. Is that okay so far? Okay, tangent of pi is 0. Well, that was nice. So negative square root of 3, we got 0 minus pi. Let's see, tangent of 5 pi over 6, we have sine 5 pi over 6 over cosine 5 pi over 6. Sine of 5 pi over 6 is 1, and cosine of 5 pi over 6 is negative square root of 3 over 2. So we have a negative 1 over square root of 3. So we've got minus that negative, we'll make it a plus 1 over square root of 3. And that will become a plus 5 pi over 6. We have to clear some room here. Okay, so let's see. We have a negative square root of 3. 5 pi over 6 minus pi is I got Pauline here all of a sudden.
Negative pi over 6.
Thank you. And we still have the 1 over square root of 3. So when we distribute, there's our pi square root of 3 over 6 minus 1. Oh, look at that. Just a negative of what we got there. Kind of interesting. Okay. Well, gentlemen, we did it. We did the impossible. See, I'm giving you, so we're working on that assignment. I'm going to go ahead and stop the video. Do you want a hard copy of that?
Yes.